One of physics' most, well, mind-bending ideas, the concept that a tiny particle, like an electron, can actually be in two places at once, in a very real sense. We're going to tackle the double-slit experiment. Richard Feynman, the Nobel laureate, he famously called it, let me get this right, a phenomenon which is impossible to explain in any classical way, and which has in it the heart of quantum mechanics.
Hmm.
So the paradox for you, the listener, to really chew on is this. How can an electron, which we usually picture as this tiny little point, how can it also act like a wave big enough to go through two separate slits and then interfere with itself? It sounds impossible. So our mission today, our goal, is to build up a coherent explanation. We want to unpack this, starting from first principles, and we'll stick strictly to, established physics, actual experimental results. Let's see if we can make sense of this apparent contradiction.
Exactly, and we'll do it step by step, systematically. We'll look at how this seemingly paradoxical behavior just naturally falls out of quantum laws. It's a necessary consequence, really. We need to explore where the electron's wave nature even comes from, look at the math that describes it, don't worry, conceptually, and then how it manages to pass through both slits simultaneously. And crucially, why does that wave behavior just vanish when we try to look? When we observe it? We'll even briefly touch on the different philosophies, the different ways people try to make sense of what it all means. Think of this deep dive as, well, maybe a shortcut for you. A way to get well-informed about one of the biggest, strangest mysteries in modern science.
Okay, right. Let's dive in then. That fundamental question first. Particle and wave. An electron. How does that even begin to work?
Yeah, it's the bedrock, isn't it? It all goes back to Louis de Broglie, 1924, a truly revolutionary idea. He basically said, look, maybe it's not just light. Maybe all matter, everything, has wave-like properties too. Every single particle he proposed has a wavelength associated with it. We call it the de Broglie wavelength now. And importantly, it's inversely proportional to its momentum. So more momentum, smaller wavelength.
Ah, okay. So for big things like, I don't know, a baseball,
Yeah.
its momentum is huge, so its wavelength must be absolutely tiny.
Exactly. So incredibly tiny that you'd never, ever notice any wave effects. It's negligible, practically zero for everyday objects.
Which is why we don't see baseballs diffracting around corners or interfering with each other like light waves do. Makes sense.
Precisely. Yeah. But now think about something incredibly small, like an electron. Its mass is tiny, so its momentum can be small enough that its de Broglie wavelength becomes, well, significant. It can actually be comparable to, or even larger than, the size we might imagine for the electron particle itself. So you just can't think of it only as a little billiard ball anymore. You have to account for this wave nature. It's fundamental.
Okay, so it has a wave nature, but what is waving? Is it like, ripples on a pond, physical wave?
Oh, good question. That's a really common point of confusion. No, it's not a physical wave in that sense, not like water or sound. The wave we talk about in quantum mechanics is, well, it's a mathematical thing. It's called the wave function, usually written with the Greek letter psi. And this wave function, it doesn't tell you where the electron is with certainty. Instead, it tells you the probability of finding it somewhere. More specifically, the square of its amplitude gives you the probability density, the likelihood of detecting the electron at any given point in space, if you were to measure it.
Okay, hold on. So before we measure it, the electron isn't actually at any single specific spot. Its location is sort of smeared out, described by this wave of probabilities.
That's exactly it. It exists in a state of potential, described by this probabilistic wave. It's not deterministic like classical physics. And this brings us right back perfectly to the double slits. When you fire an electron towards those two slits, its wave function, if its wavelength is large enough to span both slits, doesn't just pick one slit, it sort of does both. It enters what we call a state of quantum superposition.
Superposition. I've heard that term. Does that mean it's literally going through both paths at the exact same time until we look?
That's a pretty good way to think about it, yes. The wave function effectively propagates through both slits. It explores both possibilities simultaneously. And here's the really wild part. The interference pattern you see on the detector screen, that pattern of bright and dark bands, it emerges because the two parts of the electron's own wave function, the part that went through slit A and the part that went through slit B, interfere with each other. Just like two overlapping water waves create ripples.
So wait, each electron interferes with itself, even if you send them through one by one,
Right.
by one?
Yes.
Right.
That's the absolute core of it. You send them one at a time, and each electron seems to know both slits are open. It interferes with itself. Over time, click by click, electron by electron hitting the screen, that interference pattern builds up. It proves the wave nature and the self-interference.
Mind blown.
Okay.
But then there's the other part, the part that always gets me. If you put a little detector near one of the slits, just to see which slit the electron went through, poof, the interference pattern vanishes completely. And you just get two clumps on the screen like you were firing tiny bullets. It behaves like a particle again. It's almost like it knows we're watching. How does that happen? Is it consciousness?
The observer effect. It's often framed that way.
Yeah.
But no, it's not about consciousness or a mind observing it. It's about information and interaction. The key concept here is quantum decoherence. It's maybe the most crucial piece for understanding this whole puzzle. The moment any physical system interacts with the electron in a way that could, even in principle, reveal which way information, whether it's a sophisticated detector or just a stray photon bouncing off it, or even an air molecule it bumps into near the slits, that interaction changes everything. The electron's quantum state, its wave function, becomes entangled with the state of that detector or that photon or that air molecule. They become linked.
So it's not some kind of stooky action. It's a physical process. An interaction leaks the information.
Precisely. Think of it like this. The electron's wave function holds information about its potential paths, specifically the phase relationship between the path through slit A and the path through slit B. That phase relationship is what allows interference. But when an interaction happens that records which path was taken, maybe the detector clicks or the photon scatters differently, that which way information is now encoded in the state of something else. It's out there, in the environment. That process effectively destroys the delicate phase coherence between the two paths in the electron's wave function. The superposition is lost, the system is no longer isolated, information is leaked out, and without that coherence, you can't get interference. The electron is forced, essentially, to choose a path, and it behaves like a classical particle.
Okay, wow. So the math works, it predicts all this flawlessly.
Yeah.
But what does it mean for what reality actually is? We sort of mapped out the physics, but the interpretations, they try to answer what's really going on underneath. That seems like a whole other can of worms.
It absolutely is. And this is where physics starts to brush up against philosophy. Because, as you say, the math works beautifully, but how do you interpret what the math is describing? We have different stories, different interpretations, like the Copenhagen interpretation, maybe the most common one taught initially. It basically says the wave function is the whole story until you measure, and then it suddenly collapses into a definite state. Why it collapses is, well, debated. Then you have things like the de Broglie theory or pilot wave theory. It suggests particles always have definite positions, but they're guided by a real physical wave function, a sort of hidden variable. And there's the many worlds interpretation, which says there's no collapse at all. Every time a quantum measurement could happen, the universe splits. All possible outcomes happen, just in different parallel universes.
Okay, wait. So Copenhagen, Bohm, many worlds. They all predict the same results for the double-slit experiment. They all match the data we see.
Yes, that's the crucial, almost maddening part. They all perfectly account for the experimental results we've discussed, the interference, the loss of interference with measurement, but they paint radically different pictures of the underlying reality, a collapsing wave, hidden guiding waves, or constantly branching universes.
So here's where it gets really interesting then.
Right, and it raises this profound question, really for you, the listener, to ponder. If these fundamentally different views of reality, these different stories, can all perfectly explain the same observable phenomena, what does that tell us about the nature of scientific explanation itself? About the limits of what we can truly know about the world? And maybe what amazing possibilities might still be out there, just beyond what we can currently grasp?
It really forces you to confront it, doesn't it? This deep dive, this experiment, it pushes us to accept a universe that's just fundamentally probabilistic at its core, deeply interconnected, where observation isn't passive and just. Far, far stranger than our everyday classical intuition could ever prepare us for. It's quite something.